Good afternoon. As announced during the previous lecture, today I will present a proof of this proposition, which says that the difference between this sort of second order covariant derivative and this other second order covariant derivative is equal to the Gauss curvature times the length of this vector times the vector R90W. Let's start observing that if W is a vector field, then for any point of sigma u, where sigma is a surface patch which appears here, and u is the domain of sigma, then we can write that W is equal to AP times sigma u at P plus P at P sigma V at P, where A, B are small functions. The structure of the proof is the following. First, we prove that the formula is true for W equals sigma u. Second, the formula is true for W equals sigma v. And third one, the formula is true for any W. Which is of course tangent to the surface S. This fact, the third statement, follows from the fact that we can use lemma uh, 5.39, which is about the algebraic properties of the covariant derivatives. And which allows us to prove that the left-hand side of the formula we want to prove is equal to A dv du minus d du dv sigma u plus b times this operator times sigma v. Since the formula holds true for W equals sigma u and W equals sigma v, then from this composition we get that the formula holds true for an arbitrary vector field W tangent to S. So it remains to prove that the first two statements are true. Of course, the proof of the first one is similar to the second one, so I will show only that the first statement is true. So proof of 1. We start from the fact that du of sigma u can be written as gamma 111 sigma u plus gamma 112 sigma v. This follows from the definition of Christoffel symbols. Then this implies that TdV of d, sorry, I should write this better, ddu sigma u. This is using once again lemma 5.39 that gamma 11 v sigma u plus gamma 111 d dv sigma u plus gamma 112 v sigma v plus gamma 112 ddv sigma v. So I got 4 terms. Now I use again the definition of Christoffel symbols and I expand these 2 terms, 1 and 2. And I get gamma 111 v plus gamma 111 gamma 121 plus gamma 112 gamma 221 sigma u plus gamma 112 v plus gamma 111 gamma 122 plus gamma 112 gamma 222 sigma v. We do the same for ddu dv sigma u, and using the same technique we find gamma 121 u plus gamma 111 gamma 121 plus gamma 121 gamma 122 sigma u plus gamma 122 u plus gamma 121 gamma 112 plus gamma 1, 2, 2, gamma 1, 2, 2, sigma v. Now I subtract this one from this one, and I get d d v d du sigma u minus d d u d dv sigma u, using proposition 5.54, minus fk sigma u plus ek sigma v. Then I factor out k, and I get k is sigma v minus f sigma u. And now I use the definition of E and F. So I use that E is sigma u multiplied by itself, and F is sigma u sigma v. So this means that I can write this one as k times sigma u length squared sigma v minus sigma u sigma v sigma u. And now I factor out this function k sigma u length squared sigma v minus sigma u sigma v sigma u divided by sigma u squared. And now we realize something nice. This is just the projection in the direction orthogonal to sigma u of sigma v. So this is just k sigma u length square times the projection, the orthogonal projection of sigma v. Now we want to play with this formula and to prove it is equal to k times the length of sigma u cross product sigma v multiplied by the rotation by 90 degrees of sigma u. And the idea for doing this is that we we multiply and divide this function by its length, this vector by its length. So I have sigma u squared times the length of sigma v orthogonal times sigma v orthogonal divided by its length. And in order to save time, I do also another thing. I write sigma u length squared as the length of sigma u times the length of sigma u. Now, let's observe what is this. Suppose that this is sigma u. Suppose that this is sigma v. Then sigma v orthogonal length is the length of this vector and the product of these two numbers is nothing but then the area of the parallelogram spanned by sigma u and sigma v. Or in other terms, is the same as sigma u cross product sigma v length. Then I have to multiply by k on the left, and it remains to understand what is this. It is clear that this is a vector of length 1 pointing into this direction. So I use another color, points this way, for example. Sigma v orthogonal divided by sigma v orthogonal length. And then I multiply this vector of unit to 1 by this number. And for example, I get this one. This is a vector having length equal to sigma u. And now it's clear from the picture that this vector here is the vector that we obtain from sigma u applying a counterclockwise rotation by 90 degrees. So this is R90 sigma u. And this is the end of the proof, because we proved that the formula holds true for sigma u. The next goal of today is to present the Gauss-Bonnet theorem. This theorem exists in two versions. The first one is the local version, which applies to region of surface S, which are contained in the image of a single surface patch and bounded and are bounded by a closed piecewise regular curve. I will give more precise definitions later. And this version says that the integral, the sum on I from 1 to n of the integral from ti plus 1 of kgt dt, where kg is the geodesic curvature and a equal t1, t2, t3, tn equal b, is a partition of AB, which is the domain of definition of this curve here, plus sum on I from 1 to n of alpha I, where alpha I are the sine angles. This is equal to 2 pi minus the integral on R of k dA, where R is the region we are considering. And there is also the global version, which applies to regions like this, let's say bounded by piecewise closed piecewise regular curves. So the difference between this version and this one is that I don't need the region to be covered by a single surface patch, and the boundary of the region is not just one curve, but can be the union of more curves. So in order to be clear, I can make a picture. Suppose that this is a surface, then the local version of the Gauss-Bonnet theorem applies to regions like this. Instead, the global version apply, for example, to regions like this. Okay, so let's talk about the local version. Let's start by presenting the necessary definitions. So let S be an oriented surface then a subset R contained in S is called a region of S if it equals the union of an open set and the boundary of this open set to a regular region in S is a compact region are contained in S whose boundary denoted by this symbol equals the union of the traces of finitely many non-intersecting piecewise regular simple closed curves in S each trace is called a boundary component of R. 3. Let R be a regular region in S. Parameterization gamma from AD into R of a boundary component of R is positively oriented if R90 gamma prime T points into R for all T in AB that do not correspond to vertices. So this is the definition which replaces the definition of region which lies on the left as we traverses gamma. This last definition may not have a sense if we work on a surface. So forget the definition. We say that the parameterization is positively oriented if R90 gamma prime points into R. The reason why we write also that T must not correspond to vertices is that the boundary component is a piecewise regular. So it looks like this. And we have to pay attention to the fact that this derivative doesn't make sense here, 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 and here. We use also the expression of polygonal region. And this means a region covered by a single surface patch sigma and sigma inverse R equals the interior plus boundary of a piecewise regular, simple, closed, curve in R2. So now I can state the theorem I will prove. Local Gauss-Bonnet theorem, which says that let S be an oriented regular surface and R containing S a polygonal region whose definition has been given here. Let gamma be a unit speed parametrization sorry, I omitted erroneously something. I should write positively oriented parametrization of the boundary of R with sine angles alpha I then sum on I of the integrals from ti to ti plus 1 of kg t dt plus the sum of the sine angles is equal to 2 pi minus this surface integral. I would like to recall the definition of sine angles for those who forgot it. Precisely, I need, recall, a reminder, sine angles. If you have simple closed curves, which is a piecewise regular, then this curve has corners, and like this one. At each corner, you have two velocity vectors. So at each corner or vertex, as you want, there are two velocity vectors, v minus ti, v plus ti, defined as the limit as h tends to 0 from the left or the right. So if you want to compute this velocity vector, you take the minus sign. If you want to compute the second velocity vector, you use the plus sign of gamma ti plus h minus gamma ti divided by h. Here ti is the values of the parameter t for which gamma t coincide with the corner you are considering. The signed angle is defined such that its absolute value equals the smallest determination of the angle between v minus ti and v plus ti, and the sign of this signed angle is positive if v plus ti is a counterclockwise rotation of v minus ti, and it is negative if it is clockwise. Okay, let's see the proof of the theorem. So let sigma be the surface patch such that R is contained in V. So V is the image of sigma. And by hypothesis, R is a polygonal region contained in the image of a single surface patch, so this makes sense. So by definition of polygonal region, gamma tilde T equals sigma inverse of gamma T, where this is the parameterization of the boundary of R, T in AB, is a piecewise regular simple closed curve in U that bounds R tilde equal sigma inverse of R. We assume that sigma is compatible with the orientation of S. Remember that by hypothesis S is oriented. This sentence means that the normal vector that you can define using the surface space sigma coincide with the normal vector you already have on S. So that gamma tilde is positively oriented. Since gamma tilde is a curve in U, which is an open set in R2, then we can write gamma tilde T equal U of T V of T. And we call C tilde the trace of gamma tilde. For every point Q in the open set U, we define XQ equal sigma UQ over its length, and Y at Q equal R90 XQ. So we define these two vector fields. It's clear that they provide a basis for TQS, T sigma QS, and this is positively oriented because of the definition of Y. So this is positively oriented orthonormal basis of T sigma Q S. Now suppose that I is one of the interval of the form ti plus 1 on which the curve gamma is regular, and we define x of t equal x gamma tilde t, y of t equal y of gamma tilde t. And if we follow the proof of proposition 2.3, we have that there exists theta smooth such that gamma prime t, this is cosinus of theta t xt plus sinus of theta t times y of t for all t in I. The difficulty of the proof consists in proving the following statement: Kg, the geodesic curvature, is a theta prime plus this inner product. Once we do this, the second important step of the proof is the following. Is this: since the geodesic curvature can be written as a theta prime plus something else, then instead of proving that the sum on I from 1 to n of this integral is equal to something, then we work with theta prime. And the third step is to prove that the integral of this term is the one which provides the second term of the right-hand side of the formula we want to prove. So let's start from 1. Let's prove that this is true. So we define, we found that gamma prime is equal to this. Then what happens if we look at gamma second? We have to use the chain rule. This means that we will get 4 terms. The first 2 terms involves the derivatives of theta prime, of theta, that is theta prime, and the last 2 terms involves the derivatives of x and y. Precisely, you find minus theta prime sinus of theta. Here I am dropping the dependence on t, so I don't write t in the next formula. Now observe that this can be written as theta prime times the vector R90 gamma prime. Observe what gamma prime is, and remember that R90 of a vector component AB. Okay, let's say R90 of AB is minus BA. So this is a vector component cosinus of theta, sinus of theta, and the basis x, y. And then R90 gamma prime is a vector component theta prime sinus, sorry, R90 gamma prime is a vector component sinus of theta and cosinus of theta, plus something else, which is cosinus of theta x prime plus sinus of theta y prime. Now we are interested in the computation of the geodesic curvature. The geodesic curvature is given by gamma second times R90 gamma prime. Precisely is the tangential component of gamma second. So I can write this way. And if you replace gamma second, which is here, into this formula, you will get theta prime R90 gamma prime this is the first term plus cosinus theta x prime plus sinus theta y prime multiplied by minus sinus theta x plus cosinus of theta y, where once again I get here R90 gamma prime. I did not show the details for, I left them for you. Then it remains to multiply these two vectors. It is clear that this is just theta prime, because gamma is a curve parameterized by arc length. So this is a vector of length 1. Consequently, also R90 gamma prime is a vector of length 1. When you multiply this vector by itself, you get the length of gamma prime square, which is 1. So I get theta prime plus and now I have to multiply this vector and this vector. In order to do this, we will use, okay, I just write down the result is x prime y. How to prove this formula? When you will multiply these two vectors, you will find four terms involving these four inner products. Now observe that the final formula says that only this term survives. Why? These and these are 0 because this is a constant equal to 1. Consequently, the derivative with respect to t of this is equal to 0. But this is 2 times x prime x. So this is 0. For the same reason, this is 0. And what about this term here? You use the fact that x, y is 0 because these two vectors are orthogonal. Consequently, also this is 0. But this is x prime y plus y prime x. And this means that y prime x is a minus x prime y. So everything, this inner product here can be written in terms of x prime y only, and it is equal to x prime multiplied by y. Okay, let's erase. So we completed the proof of the formula. Okay, g equals theta prime plus x prime y. Now let's prove that that this is true. There are two cases to be considered. One, okay, let's write A. Sigma is conformal. Two, sigma is not conformal. What does it mean, conformal? So, definition, a diffeomorphism F between two surfaces is conformal if this angle is equal to this angle for all P in S1 and all XY in TPS1. Sigma is not a map defined between two regular surfaces, but you can use anyway this definition, which is a definition 3.70. Why? Because the domain of sigma, which is an open set over 2, can be seen as a regular surface. So I can keep using this definition here. Okay. One moment. If I cannot find If the map sigma is conformal, this means that the curves gamma and gamma tilde, which has been defined in the following way. I want to find the formula. Give me a moment. What is the formula for um, yes, I found where gamma tilde t is sigma inverse gamma t, share the same sine angles at the corners, and the same angle function theta. So this means that I can use theorem 2.7, generalized of Umlaufsatz which says that I'm looking for statement of the theorem, but I cannot find it. One moment. I had hit. Yes. Because Ks is equal to Kg. So it remains to handle the non-conformal case. We look at the proof of this theorem, and the idea is that we replace a corner by an approximating small portion of smooth curve. For example, if you have this, then you replace it by this, so this corner disappears, and now the curve becomes smooth and regular. So this implies that there exists a single smooth function angle function theta defined on AB before we had a function theta defined on an interval of this form. Now we have a function theta defined on the entire interval AB. And if you have this, then you can write that integral of this function, which is theta b minus theta a, this is 2 pi times the degree of the map t sent to cosinus of theta t sinus of theta t. Now we want to work with the map related to gamma tilde. So we have to prove that this degree coincide with degree of t sent to gamma tilde prime t over gamma tilde prime t. And this fact follows from exercise 3.58 with G equal D sigma gamma tilde T and V equal gamma prime tilde T. I prefer not to enter the details. In order to save time. It implies that these two maps do not have output in opposite direction, and also consequence of lemma 2.4, which uses as hypothesis exactly this fact. So this is hypothesis of lemma 2.4. And now we have finished it because we have to apply op Lausatz to get that the degree of the map which sends T to gamma tilde prime T over gamma tilde prime T length is equal to 1. And what is the consequence of all of this? That the integral from A to B of theta prime T equal theta B minus theta A, this is just 2 pi. And this is exactly what we needed. Some of you could ask, where is this term? This term disappeared because of the smoothing. And if you want to know more, please look at the proof of theorem 2.7. Okay, now let me check how much time I have. Not that much. Okay, so it remains to prove that integral sum on I of integral from ti to ti plus 1 of x prime t y t dt is equal to the integral over r of k dA. For proving this, we use Green theorem. Along gamma theta to the vector field F defined on nu with values in R2, defined this way. F equal xu y xv y. Now I want to recall the statement of Green theorem. It's a theorem that you may have studied during the Calculus 2 course. And in this textbook is stated as theorem, presented as theorem 2.32. So it says that if F equal PQ is a vector field defined on an open set containing the interior of a positively oriented piecewise regular simple closed curve in R2 and the curve, let's give a name to the curve, let's call it C. Then this integral here is given by the integral over d of qx minus py dA. Okay, so let's call P this function and Q this function. Then since x prime is nothing but an u prime x u plus v prime x v, then the integral from ti plus 1 of this inner product here. Okay, instead of working with ti to ti plus 1, I will work as the integral from a to b, paying attention to the fact that this means the sum on I of the integrals from ti to ti plus 1 of the function. This is nothing but then the integral along C of f d gamma tilde. And by Green's theorem, this is equal to the integral over r tilde of qu minus pv du dv. So please prove by yourself that this integral here is exactly the integral of x prime y dt. Okay, now let's expand this function. This is the integral of xv y u minus x uy v du dv. Now, if you differentiate with respect to u and with respect to v, this function, after simplification, you will get that this is equal to xv yu minus xu yv. And then here I will just multiply and divide by this area distortion. And it remains to prove that this is equal to minus Gauss curvature and this is equal to minus the double integral over r of kdA. So it remains to prove that this is true. So proof of minus k equal xv yu minus xu yv. Let's observe the following fact. If we fix q in u and we denote sigma q by p, then you know that the Gauss curvature k is equal to the determinant of the matrix representing the map WP with respect to any basis of TPS. So here we have two bases. The first basis is xy. The second basis is sigma u, sigma v. Now suppose that x is equal to a sigma u plus b sigma v, and y is c sigma u plus d sigma v. So this means that the conversion matrix M between these two bases is A, B, C, D. So what is the Gauss curvature at P? This is the determinant of a matrix representing the Weingarten map with respect to a basis of TPS. Let's choose this one. Then we have minus dn px, x minus dn py x minus dn px y minus dn py y. First of all, let's observe that we can change this sign into a plus because this is a matrix of order 2 and the determinant does not change if we do this. This is equal to the determinant of what happens if we write x and y this way. It happens that we get this matrix here multiplied by A, C, B, D. The reason why at some point N of U, NU and NV shows up is that dN P sigma U is NU and dNP of sigma V is NV. These two vectors, sigma U and sigma V, will show up in this formula after replacing x by a sigma u plus b sigma v, and y by c sigma u plus d sigma v. Unfortunately, I have to erase. Now, if you use proposition 3.38, you will see that the determinant of M inverse equal 1 over determinant of M. It is equal to the area distortion of sigma. So instead of writing this way, we can write one over this term times n ux and vy and uy and vx. Okay, now I can erase this part. And I will use the following formulas. Nux is minus nxu, nvy is minus nyv, nuy is minus nyu, and nvx is minus nxv. It's easy to prove these formulas. For example, how to prove this one? You start from nx equals 0. Then also this is 0, but this is nux plus nxu. So from this identity, this one follows immediately. The proofs of the remaining three is the same. So what do we got here? We got that this is equal to, in order to save time, I could just do this. And now, what is this? This is 1 over area distortion times xu n y n minus yu n x v n. This formula follows from previous one, observing that this is nothing but an x u n. This is y v n. This is y u n, and this is, sorry, this is the length of this vector. This is the length of this, and this is x v n. And these product coincide with this inner product because these two vectors are parallel. xun and yvn are parallel because they point in the direction of n. Same reason for why this identity is true. We have then finished it. Because this is equal to 1 over distortional sigma times x u y u minus y u x v. Sorry, I made a typo. Why this formula is exactly equal to this? Once again, we use the fact that from no, let's okay, we use again equations 6.1, which is okay, I'm going back on my which says that xux is 0, xvx is 0, yuy is 0, yvy is 0. That's all. There are other equations, but I need only this one. So how to prove these formulas? The technique is the same. You start from the fact that this is a constant. So this derivative here will be 0. And this is also twice x u x, and consequently the inner product of x u and x is 0. And this formula says that only the normal component of xu matters, same with the yv, yu, xv. And if you, okay, you need to make some computation here using these facts. Please fill the details as an exercise. Essentially, you will see that the tangential component of these vectors cancel out. Now I think we finish it because we proved that this is equal to minus, I think I have to adjust the sign. Let me check again. Yes, so we proved that this is equal to k. And in our formula, we had instead minus k. So we have to make a change of sign. This is a 1 over area distortion of sigma times xv yu minus xu yv. So this is the end of the proof. Let me check how much time I have. Okay, it's very late, so let's continue with the consequences of this theorem next time. Thank you for your attention.